got my permit already. I did receive the email.
Oh, perfect. Yeah. Yeah, because I think they were processing it today. So I think they might have been going
So
up.
what should I do? Just wait the system add me on, or I have to do it?
You have to so there should be instructions with the permit. I think you have to actually add the course. I don't know if you have to drop it first or add it, but then it should say in the email what you have to do, right?
It says that you may enroll this form through your form.
Yeah, you may reach out to them again and ask what you have to do.
In some. And you mean the one. What anything. So when
Every class I'm on with, it's like they just open the class.
it's on the system, I had to do it. Yeah, I will see it. I will see the public now.
I think we might actually. I think we do.
I don't want to drop it.
Yeah.
But you can.
Yep.
If you have an ad permit, do you have to drop the class and then
Yeah, I'm not sure.
add it with the permit?
Yeah. Yeah, I'm not sure because they're doing it differently because before in the past they would just increase the capacity of the course.
And then you would slide.
Yeah, right, but then but yeah, now they're doing this permit thing. So I don't know if you have to drop it
Oh,
and
yes,
add again.
she just replied me. Yeah, drop the.
Drop it, yeah,
The
right.
word is first and then we drop.
Makes sense. Mhm.
We're here, Trina. Oh,
You
Earth
made
is
it.
coming back.
Who is?
Earth
Oh, yeah.
in February.
I'm so out of league news, but
Well, I mean, anyone can play that.
yeah, I know. It's fun. It's fun. ERP is always fun for like the first week. And then once people start try-harding, it's not as fun anymore.
It's like whatever character program.
Yeah, then everyone just uses the OP characters after that and it's like, all right.
Like Sona,
Warwick.
Yeah.
Top tier. And then Blitzcrank. I remember doing a whole Blitzcrank team. Oh no,
Like-
there was. What was the other game mode? All is one, where everyone did one champ.
Yeah.
And you're all the same.
Yeah,
That one's fun. No, Sona. Good.
I like playing Israel on that. Just snipe people. It's on PvE, right? You get your ult every 10 seconds.
Hell yeah, bucks, 10 seconds. John, I think you live on Power One. It's just funny because like everyone that plays League. Everyone that plays League, they know that.
Oh, yeah.
It's always gonna be a fun.
Yeah, my brother's been playing. My younger brother.
Oh, yeah, exactly, but, we can, I don't know, wait, we have to like, how we buy it, how we bought it. To create our own server. The last class, we're not needed to like memorize anything better.
no.
So I missed like the first 10 minutes, so I was just. Catch up.
We'll be seeing a lot of that stuff throughout the class, but it's just kind of like a first introduction and then.
Yeah.
You hear the ending?
No.
I'll let you find out.
No. It's hilarious. Bro, how does he not expect the battle? 6 tickets.
Well, the boot charge was $1,000 in itself. I should never buy it. They just said.
He got real mad. I'm not sure.
You have a photo?
Yeah, he took the photo, or I sent it to Calvin and told Calvin to show.
Oh, you gotta send that.
Wait, you saw this cartoon?
Yeah, my car was next to him. I just saw it. Like, really quickly. Send it.
What's the same?
It's a. Immobilization. United Time.
Yeah.
Get rid of Williams stuff on my list. I just drew one down, but I need that photo.
Want to pull one down?
Yeah, okay, but. I mean, I get more.
You wanted to say that.
Yeah, well, you like me. Yeah. Just gonna see that. Oh my god. Did I say the number? You might have it, 831, it'd be the only number from Sanford's. 831. Wait. 8187864, yeah. I didn't have. Oh, bro. Nah, I think Brady's gonna step. Oh, you're not, I'll skip it all. I said it's not very. I was doing it for there. You were. So what happened to my thing? You just, let Michael sound the story.
All right, it's 4 o'clock. Let's go ahead and get started. All right, good afternoon, everyone. How's everyone doing today? Good, good. All right. All right, so we're in week 2. So this is the well, originally, if you asked me over a week ago, I thought this would be the first day I would meet you guys, but you know, we've already had 2 class sessions. So the plan for today is we're going to be reviewing fluid mechanics today. So it's we're just doing a straight up lecture. You know, just because I know it's been a while since some of you have taken fluid mechanics 333. So I wanted to review some important concepts. Maybe some new ones too. Maybe some things you haven't learned in fluid mechanics before. But we're going to use a lot in this class. So today is just kind of like a recap of fluids. Okay. All right. So some announcements. I do have an answer for everyone that's on the wait list. We are limited, unfortunately, by the capacity of this room. So I was only able to add 7 people from the wait list, and so if we were top 7 on the wait list, I think the permits actually just went out, and so you should have been reached out to by the department with the permit to add the course. And so if you do get that email from the department with the permit, what you have to do is you have to drop the course and then re-add the course, you know, to the with the permit. And you want to make sure you do that very quickly because I think those permits only last 24 hours. And so if you didn't do it already, make sure you do it either right after the class or right when you get home today. Okay. And so if you didn't get a permit for the class, unfortunately, I wasn't able to add you to the class. And so if you need another technical elective, I know that there's another one offered at this time, 462. That is composite materials, and so that one is an option for you guys. But if you're having trouble finding an elective, luckily I'm also one of the advisors for us too, for our department, so you can come talk to me and then we can work something out. But I was only able to add 7 people from the wait list. So if you were top 7, you were in the course. I think there were about 5 people that were 8 through 12 on the wait list that weren't able to add the course. So I was planning on reaching out sometime, but then I got kind of busy right before the wedding. So I'll reach out to everyone that wasn't able to make it. Then I'll make sure you guys are taken care of. Okay. Whether it's another course or okay. All right, and so I also wanted to have homework 1 ready for you guys today, but something came up this afternoon. I wasn't able to do it, so I'll work on that tomorrow, and that should be posted by before Thursday. Okay. Homework 1 is mostly just going to be a review, basically just practice with review of fluids, and so just to make sure you kind of remember everything that's going on here. Okay. All right. Any questions I can answer before we get started for today? Okay. All right, so let's go ahead and get started. So the topic for today is fluid review. Right, so it'll be a little mix of both. And so, we'll be reviewing some important topics of fluids, and then we'll kind of transition to steady flow in rigid tubes. Okay. All right, so last Thursday or last time we met, we spent the entire time talking about cardiovascular anatomy and kind of the biological side, right? So remember, I don't expect you guys to memorize everything that we talked about last Thursday. It was kind of just a barrage of information. But a lot of those topics, a lot of those ideas are going to come up, throughout the course. And so I just wanted to introduce you to it so that, when I bring certain things up, later on, it'll at least sound familiar, but a lot of those things we'll talk about kind of multiple times in the course, just because it's, they're all, a lot of those are probably new. And so the first thing we're going to connect it to is fluid mechanics. Okay? And so remember, one of the last things that we talked about last Thursday was this idea of, is blood a fluid? Okay. And the answer to that is yes. And so for the most part, for at least for everything in this class, for flow in what I call kind of the larger vessels, the larger arteries, the larger veins, we can consider blood to be a fluid and behave very much like so. Okay. And as a Newtonian fluid, it follows all of our equations for fluid mechanics, most notably the Navier-Stokes equations. Which we're going to talk about a lot later on today. Okay, but we'll work our way up there. Navier-Stokes is kind of a more advanced topic in fluid mechanics. Okay. Okay, so let me draw the geometry that we're going to consider today. Okay. One thing about blood flow is that because your blood vessels are tubes, we're going to be working primarily in cylindrical coordinates. Okay, so that means our coordinates, instead of being x and y, they're going to be primarily r. Okay. R being the radial direction, so that kind of points outwards towards the vessel wall, and the z direction, which points down the length of the blood vessel. Okay. Okay. And so if this is a drawing of a particular blood vessel, let me go ahead and label this a bit more. We'll call the left-hand side of this diagram 0.1, the right-hand side of this diagram 0.2. Okay. Because blood flow is an internal flow, that means it's encased by walls on all sides. For the most part, these types of flows are what's called pressure-driven flows. Okay. And so in order to drive flow forward, in order to do that, you need a difference in pressure. And so what this means for this diagram is that, if we assume that blood is going to flow from left to right, okay, that means P1, the pressure on the left, has to be greater than P2. Okay. Remember, pressure is an expression of force, and so pressure is simply just force distributed over an area. And so if you have greater force on the left, less force on the right, then that's going to push everything in between, from the left-hand side to the right-hand side. Hence, pressure-driven flow. Okay. All right. Generally, what we're interested in this situation is the velocity of the blood. Okay. And usually we express that velocity as a function of the radius. And so the symbol that we're going to use a lot for it is UZ of R. Okay. So the U there stands for velocity. The subscript Z means the velocity is going in the axial direction, in the Z direction. And the parentheses R means that the velocity is going to change depending on the radial coordinate, okay? And so if you remember from your fluid mechanics class, typically in a pressure-driven flow like this, you have a parabolic flow profile or parabolic velocity profile. And so if you were to sketch the velocity, it would look something like this. Okay. Okay. So you have a maximum of the velocity in the center of the tube. Okay. And then at the walls, because of the no slip boundary condition, right? Because the walls are rigid, they're not moving, and the fluid that's immediately touching the walls is going to stick to it. And so you have zero velocity at the walls. So this is no slip. Zero velocity. Okay. And so if you have zero velocity at the walls, maximum velocity in the middle. The simplest mathematical form that can support this thing is a parabola. Okay. And we'll be able to obtain this kind of later on in Navier-Stokes. But kind of the reason I'm kind of giving you the preview now is to show you that as you go in the R direction, okay, your velocity value is going to change a lot. And so it goes from 0 up to its maximum. And so one of the primary goals that we're going to be accomplishing today is we're going to be solving for this. Through the Navier-Stokes equations. Or in other words, through conservation of mass, conservation of momentum. Okay. And once you obtain the velocity distribution, there's a lot of other really useful information that you can obtain. So you can obtain things like the mass flow rate, or the volume of blood that's passing through the blood vessels at any given time. You can solve for the viscous shear stress, which is a trigger for a lot of cardiovascular diseases. It can trigger platelet activation, like we talked about last Thursday. Okay. So the velocity distribution is kind of like the holy grail of just fluid mechanics analysis in general. And the way that you obtain that can vary, whether you're doing the computations on paper, or in our case later on, whether you're doing a simulation. Okay? But ultimately, a lot of times when you're doing fluid mechanics analysis, that's what you're primarily looking for. All right, any questions on this so far? Okay. All right, so before we do that though, let's go ahead and talk about just fluid properties in general. This class is a little bit unique compared to kind of a traditional fluids class because we're only considering one fluid. There's only one blood, right? And so, things like the density, the viscosity, those don't really change. We're going to be working with the same values throughout the whole class. But it's good to kind of understand what these properties actually physically mean to kind of put in context kind of a lot of the other things that we're going to describe. Okay, so let's start basic. So let's start with kind of the definition of a fluid. So a fluid, at least in the way it's defined in terms of Newtonian mechanics, is a substance that continuously deforms when under an applied force. Okay? And the key word here is continuously, right? When you compare this to a solid, right? So if you have a solid object and you apply a force to it, and assuming you're kind of in a static situation, the solid object will deform, right? It's going to either, squish, or it's going to stretch, or it's going to compress, right? but it only deforms once. And so once it's kind of deformed, it reaches its equilibrium state and it stays. For a fluid, as long as you're continuing to apply a force, that fluid is going to continuously deform. Okay. We have another word for this because no one says continuously deform. No one says the water is continuously deforming out of your faucet. What we say instead is that your fluid will flow. So flow is kind of the informal term that we use for describing how fluids deform. Okay. Okay. And so the way that we describe this, or the way that we kind of quantify it kinematically, is through its velocity, kind of what we just described. Okay. In particular, the term that we use sometimes is called velocity field, which tells you how the velocity changes as you go to different points in space in the fluid. Okay. Okay. And so, for instance, if we were to just look at kind of flow in a box, and so let's say that we're looking at a fluid from above. And if we were to drop sensors in this fluid, so if we were to have, little sensors like this, where each sensor can measure the velocity of the fluid as it flows past it. Right? And so if we were to let fluid flow through this box, what we would eventually see is that each marker we'd be able to get an arrow. Okay? And so on and so forth, right? So each arrow shows the magnitude and the direction of the velocity at different points within the box. Okay. Let me actually fill the rest of this in. So maybe it looks something like this. And so if you were to trace this out, and so if you were to kind of follow the arrows and use kind of a different color, you may look something like this. Okay. So that's how you kind of visually kind of see the flow. And so the idea with the velocity distribution, and so in this case, we have a u that's a function of x and y, okay? Where each marker has a different x and y location, right? Each marker will give you the magnitude and the direction of the velocity. Remember, velocity is a vector. And so not only do you need its magnitude, you also need to know which direction it's pointing as well. Okay. So this is kind of a visual representation of a velocity field. So of course, this is a 2D case, and so we have two space dimensions here. For the most part, or at least kind of what we can solve by hand, for the most part, we're limited to just 1D cases. But just know that you can have velocity fields in 2D and 3D as well. You can even have unsteady cases too. So not only do they vary with 3 spatial dimensions, but they're also going to vary with time as well. Okay. So these get very complicated very, very quickly. And even a lot of the 1D cases are very difficult to solve by hand. Fluid flow is hard. Fluid mechanics is hard. That's why it's we have to rely on computers a lot to help us out. Another name for velocity field, I try to keep my terminology consistent, but sometimes my mind just kind of turns off. Another name for velocity field, you'll hear me call it a velocity distribution as well. So those two are interchangeable. Velocity field, velocity distribution, they mean the same thing. I'm gonna try to use velocity field, but sometimes sometimes I'll just kind of default to velocity distribution because that's how I learned before. An old habit style. All right, so if you relate this to kind of what we started talking about today, ultimately what we're looking for is this UZ of R. So UZ of R, that's the velocity distribution. Very good. That's the velocity field inside the blood vessel, except it's only a one-dimensional case here. So our only spatial dimension here is just the R. Okay. But in reality, velocity is a function of all variables in space. Okay. All right, any questions on this so far? Okay. All right, so let's talk their physical properties now. So velocity is important to know, but velocity is not really a property of the fluid itself. It's not a material property. Let's talk about the material properties of the fluid. So fluids have a lot of properties, even a lot to do with just pure fluid mechanics, but they also have thermal properties. They also have lots of chemical properties, things like that. We're mostly just going to focus on its two main fluid mechanical properties, which is the density and the viscosity. So let's start with density. Okay. Density is an expression of mass. But the thing with fluids, because they're constantly moving, it's difficult to describe the mass of a fluid using just mass. Because if you're talking about things in terms of kilograms, in terms of grams, that means you're looking at a fixed amount of mass, fixed amount of material, whatever you're looking at. But because fluid is constantly moving, things are always crossing boundaries, things like that. It's difficult to describe the mass or the weight of the fluid in terms of just raw weight or mass. So instead, we do a ratio. So density is the main way that we describe this. Okay? So density describes the relative weight or mass of a fluid per volume of fluid. Okay? And so the definition for density, mathematically, we give it the symbol rho, and so it's kind of a slanted p, slanted lowercase p. Okay? It's the mass of a substance divided by the volume. Okay? So density is important because density is a measure of an object's inertia, right? And so think about kind of how you understand inertia from solid mechanics. So inertia is an object's ability to resist changes in motion, right? So if an object has a lot of inertia, so let's say it's an F-150, a giant pickup truck, right? A pickup truck is massive. So if you were to try to push it, with your hands, it'd be really hard. Not impossible. It's impossible for me because I'm really weak. But if you're strong, even if you're stronger than me, it would still be really hard. And so for a fluid has the same also has inertia because it's made of mass. But instead of using mass, we use density. The density expresses okay. So the more dense a fluid is, the more inertia it's going to. Okay. So what about blood? So where is blood kind of along the density spectrum? Well, it turns out, in terms of density, blood is actually not that different than water. So the density of blood and water are very similar to each other. Blood is just very slightly more dense than water, just because blood has all these kind of red blood cells and platelets and stuff inside there. So, um, but all those little particles, those cells and stuff are very, very light, and so it makes a very, very small difference. And so, actually, what you'll see is that a lot of experiments that try to mimic blood, a lot of them just use water. And if you're not taking viscous effects into account, that's pretty good actually. So density, between blood and water is very, very similar. So if you had like a liter of blood and a liter of water, and you close your eyes and you try to pick them up, it would be very hard to tell the difference. Okay. All right. Any questions? Any questions on that? Okay. All right. So that's density. Density, pretty straightforward. Um, the next property that we want to talk about is viscosity. So this is where things get a little bit more interesting. Okay, so the viscosity, I think viscosity is one of those things where it's kind of easier to describe informally first, and then kind of get into a more formal definition. So viscosity kind of describes the fluid's ability to kind of be sticky or to feel thick. This is- And so fluids that are highly viscous, fluids like honey, fluids like molasses, all of those come to mind when you're talking about viscosity, right? And so, honey feels really sticky. So if you stick your hand into like a jar of honey, it's going to feel very like it's like you can't really pull your hand out because all the honey is kind of clinging to your hand. Okay. Um, so more precisely, and I'm kind of waiting for my iPad to catch up here because I think the internet's lagging a little bit. More precisely, the viscosity describes the relationship between shear stress and strain rate in a fluid. And so the relationship between these two things is very important for fluids. Okay. All right, so to visualize this, let's look at a parcel of fluid. So let's look at a rectangular parcel because it's a little bit easier to kind of illustrate these concepts that way. So we're looking at just a snapshot, right? And so, let's say that we have a fluid that's flowing, but we take a snapshot and we kind of draw with our, with the pen, kind of a rectangular parcel of fluid. Okay. And so, as the fluid undergoes motion, this parcel of fluid is going to be exposed to shear stresses. Okay. Okay, so we're going to have shear stresses on the top and shear stresses on the bottom. So tau here is shear stress. And the reason those shear stresses arise is the fact that, is from our velocity field. And so different parts of the fluid are going to be experiencing different velocities, right? And so when you have kind of one layer of fluid that's experiencing one velocity, okay, so let me actually kind of draw that. So let's say that we have one fluid here, one layer here, and another layer here. Okay, we'll call the top layer layer 1, the second layer layer 2. Okay, they both may be going in the same direction. So let's say they're both going to the right. Okay, so let's say that the top layer is going to the right with the velocity v1. The second layer is going to be going at a velocity v2. Okay, and if v1 is not equal to v2, right? Which is the case a lot of the times in fluids, right? And so you have situations where you have different velocities at different locations. Okay. In this case, what's going to happen is you're going to have a shear stress that develops between those two layers, between those two locations. Let's take an extreme case. So let's say that one layer is stationary. So let's say that V2 is 0, okay? But V1 is going to be greater than 0, okay? And so in the case you have a stationary plane and a non-stationary plane moving past each other, okay? And this is something you can feel. And so if you take your hands, okay, put them together, make your right hand still and just move your left hand across it, right? You should feel that your hand kind of heats up a little bit, right? And that's due to the shear stresses and the friction that occurs between those two layers. Okay. The only difference in a fluid is that this is happening on kind of micro scales, kind of microns to microns, and kind of in all different directions too. Okay. And so shear stresses is something that's very, very prevalent in fluid mechanics. Okay. And so if you continue shearing this parcel of fluid, okay, or in other words, we're going to let this flow develop. Okay, what's going to happen is that this parcel of fluid is going to become deformed. Okay. And so if we have the shearing stresses kind of in the direction that I indicated up there, you're gonna have that top layer of the box going to go to the right and the bottom layer of the box and go to the left. And so you're going to get like a parallelogram kind of situation here. So it's going to be something like this. And so the whole thing is kind of become deformed. All right. And so one way that we can quantify this deformed state is if we measure this angle right here. So I've redrawn kind of a vertical line, and I've drawn this angle here, okay, this angle here kind of expresses how much this parcel has deformed. But of course, an angle here has no units, and so what we could say here is that this angle here represents the strain. Strain of this parcel, okay? Because a strain is nothing more than just a relative deformation, right? An angle kind of represents the same. All right, and so if we take the strain and we take its derivative, okay? And so the rate at which the strain of this parcel is changing, this is the strain rate of the fluid. And if you look at the units for this derivative here, and so up top we have a d theta, so the theta has no units, and so we have nothing up top. And on the bottom we have a units of time, right? So dt is time. And so the units for this is 1 over, well, you're not supposed to favor one measuring system, but SI clearly is the superior measuring system. Okay. So the SI units for this would be 1 over seconds. Okay. Although I guess to be fair, English units uses seconds too. All right. So that's good. So now we have an expression for the strain rate, and we kind of have an idea of kind of how it comes to be and how it and what it kind of quantifies in fluid. Any questions on this so far? Okay. All right, so this is good. So, ultimately, just to kind of remind you, we started this discussion talking about viscosity. It doesn't seem like it, but we're still doing it. And ultimately, we want to form this relationship. And so what we said was that viscosity forms the relationship between shear stress and strain rate. Okay. So we have one piece of the puzzle. So one piece of the puzzle is the strain rate. Okay. But right in this current form, it's not useful. Okay? Okay. Because in order to use this, we need to obtain the strain for the for fluid. And unless you have a very high-speed camera, that's very, very hard to do because you have to follow kind of the same parcel of fluid, and you have to do this at all locations, and it's just not practical. There are ways to measure it, but it's not that useful. Okay. And so the question is, can we express the strain rate of this fluid in a form that's more convenient for us to use in computations? Okay? Keeping in mind its units, right? And so that's kind of the reason I brought up the units here. Just because, I'm going to give you another expression here, and we're going to see that it has the same units as the problem. Okay. So let's try this. And so instead of d theta dt, let's express the strain rate in terms of velocity. Okay. So velocity, if you remember, has units of length over time, so meters per second. Okay. That's the SI unit for velocity. Okay. And so if we make the expression and we kind of use the same we use a derivative, right? So very similar to its other cousin, right? So if we take the spatial derivative of velocity, so du dy, what we see is that this has the same units as above. So velocity here up top has units of meters per second. Okay. If we're taking a space derivative, then we're going to be taking on the bottom here, we have a units of length. Okay? So there's meters, meters going to cancel out. And so it's going to be 1/second. Okay. And so this expression right here is the more standard form for strain rate in a fluid. Okay? Okay. This is generally much easier to work with because if you're doing experiments and you're measuring velocity, it's you can just take the velocity and just take its spatial derivative. If you're solving the equations, if you're solving Navier-Stokes, you're naturally going to get the velocity out of it anyway, and so it's easier to use in that sense. And if you're running simulations, if you're running CFD, you'll obtain the velocity field from your simulation, so you can compute the strain rate from that. And so this gives you the exact same thing. It's just much easier to use than d theta dt. Okay. Okay. So that's the strain rate. And so what we said was the viscosity is the relationship between strain rate and shear stress. Okay. So shear stress, if you remember, that's kind of where we started. Shear stress is the force that's experienced within the fluid, okay, that arises due to the fact that you have differences in the velocity, okay. And so our expression for viscosity looks like the following. So we have shear stress on the left. On the right-hand side, we have du dy. So this is our strain rate. And this, and then this little guy right here, this mu, this is our viscosity. So that's our viscosity relationship. So, the shear stress and strain rate very closely related in a fluid. And the kind of the almost like you can almost think of it like a proportionality constant or a coefficient that relates them is the viscosity. Okay. Viscous relationship. Okay. And so the higher the viscosity, the greater amount of shear stress that you're going to experience. Okay. And so if you look at honey, if you have large changes in velocity as honey flows, that's going to generate very high shear stresses because of the viscosity. Okay. Another way to look at this is that the strain rate here is also kind of an expression of flow. Okay. And so the higher the strain rate, generally the higher your flow or the faster your velocity. Okay. And so another way to interpret this equation is that if you have a highly viscous fluid, in order to get it to flow more easily or with a high speed, you have to apply a lot of force or you have to apply a lot of shear stress in order to make that. Okay. So lots of different ways to interpret this, very simple formula and kind of with a lot of implications. Okay. Of course, the caveat here is that, this equation is only valid for Newtonian fluids. Okay. We touched briefly about Newtonian fluids last time. So a Newtonian fluid, for all intents and purposes, you can think of it as just like a normal fluid, a fluid that behaves normally. So like water, air, engine oil, right? So cooking oil, vegetable oil, olive oil, these are kind of like normal fluids that all follow the rules of Newtonian physics. Okay. Of course, you know, blood technically not a Newtonian fluid. It is a shear thinning fluid. And so a shear thinning fluid basically, what that means that the more shear or the higher amount of force that you expose to the fluid, it actually thins out. And so the velocity, the viscosity actually goes down. And that's mostly just to make sure that your blood can actually fit through all the little tiny capillaries in your body. Okay. You know, but like we mentioned on Thursday, for the most part, for everything that we're doing in this class, where we're examining kind of the larger vessels, the big arteries, aortas, you know, veins, even flow in the heart, you know, we can assume Newtonian fluid, and it's a very, very small difference. It's you know, lots of experiments. And so from here on out, you know, all the equations that we're going to be looking at, Navier-Stokes, things like that, we're going to be assuming this relationship. Okay. Okay. Any questions on this so far? Okay. So you guys have probably heard the saying that blood is thicker than water, right? And so that's been used in Hollywood and in movies for things that have nothing to do with biology. But it is actually true. Blood is thicker than water in the sense that blood is more viscous than water. Okay. And so we can see this to be true. And so if we measure the viscosity of water, so its viscosity for water, in SI units, it's about 8.9 times 10 to the minus 4 Pascal seconds. Okay. For air, and this is dynamic viscosity, by the way. For air, another common fluid, air is very non-viscous. It's very hard to contain air. Okay. So air has a viscosity of 1.81 times 10 to the minus 5 Pascal second. Okay. So different order of magnitude, but you know, it's about actually, yeah, different whole order of magnitude lower than the water. Okay. So what about blood? The viscosity of blood is about 2.87 times 10 to the minus 3 Pascal seconds. Okay. And for the most part, this is mostly constant. Right, because another way you can think of a non-Newtonian fluid is you can think of it as its viscosity changes. Okay. That's not the full definition, but it's kind of a useful one to think about. Right. So water, air, these are Newtonian fluids, and so their viscosities are going to stay constant at a fixed temperature for the most part. Blood is as well, unless you go to the very, very small scales. Okay. Okay, so it is true. It is true. Blood is thicker than water. But a more accurate statement would be blood is more viscous than water. But I think that doesn't sound as cool in movies. All right, any questions on this? Okay. All right, so let's jump into the governing equations now. So now that we have kind of an idea of the important properties of fluids, of blood flow, let's talk about how we actually solve for its solution. And so we're going to be talking about the Navier-Stokes equation. So Navier-Stokes equations, it's just like the name implies. It's named after two dudes, okay? The two dudes that figured out how fluid flow works for the most part. But a better way to kind of remember it is that Navier-Stokes is simply just conservation of mass, conservation of momentum for a fluid. Okay. So the Navier-Stokes equations are about as close as you can get to kind of like a mother equation or master equation for fluid mechanics. Okay. Which is typically the case for any kind of conservation law. So conservation of mass, momentum, energy, these are kind of fundamental laws that kind of govern a lot of our physics. Okay? Okay. And so if you can solve the Navier-Stokes equations, it's solving the Navier-Stokes equations in a general form is actually one of those $1 million questions. And so if you can solve it, there's some foundation of ridiculously rich people that will pay you $1 million for the solution to Navier-Stokes, which at this point, is I think should be worth a lot more than $1 million. Inflation is caught up. $1 million doesn't get you as far nowadays. So if you're going to be doing something massive like solving Navier-Stokes, you should at least get Jeff Bezos's rocket, at the bare minimum. Okay. So solving these equations. If you're able to solve them, and we are able to solve it in very niche scenarios, so you can't solve it in general, so you can't solve it in an arbitrary situation. But if we solve these situations or solve these equations, what we obtain from this is our velocity field for the fluid that we're considering. Okay. Which, as we've been discussing today, is very valuable because from the velocity field you can compute things like the strain rate. You can do the strain rate. You can get the shear stress. Okay, it gives you a lot. Okay, all right. So I'm going to write down the Navier-Stokes equations in one of its more simpler forms. If you've seen it before, you may not have positive memories of it. If you haven't seen it before, you're about to have a not so positive memory of it, but I love the Navier-Stokes equation. So let's just get into it. So these are the Navier-Stokes equations in Cartesian form. So if you remember from the beginning of the class today, we mostly work in cylindrical coordinates and blood flow. But if I showed you cylindrical Navier-Stokes right out the gate, then this will be a very non-positive memory. So we'll start with the simpler form, which is Cartesian. So by Cartesian form, I mean x, y, z. Okay, so those will be our main spatial coordinates. Okay. So notice how I said that I've always called them Navier-Stokes equations, plural. So there's more than one. So first we have the continuity equation, which is conservation of mass. Even my iPad getting excited. And I've gone ahead and kind of skipped to the incompressible form. And so we've already kind of assumed the fluid is incompressible. Okay. And what that basically means is that the density is constant. And so if you have a liquid state fluid, so it's not air, it's not a gas, for the most part, you can assume the fluid is incompressible, and that's typically fine. Okay. So this equation here is the conservation of mass. Or sometimes what it's called is it's called the continuity equation. We have quite a few variables here, so let's go ahead and define them. So u here is the velocity, the fluid velocity in the x direction. We have v. V is the fluid velocity in the y direction. And then we have z. Z is or w. Jumping ahead myself. W here is the fluid velocity in the z direction. Okay. And of course, x, y, and z are just, x, y, and z. Ooh, it's like a ghost is writing this stuff. All right, and so all the other weird symbols, if you haven't seen before, those are partial derivatives. And so what we're saying in this equation is that the partial derivative of u with respect to x, plus the partial derivative of v with respect to y, plus the partial derivative of w with respect to z, you add all those things together, you get 0. Okay. And if you recognize these expressions, we spent a lot of time talking about this with viscosity. These are all strain rates. And so what we're saying is that the strain rate of x of u in the x direction, the strain rate of y in the y direction, the strain rate of w in the z direction, you add all those together, they have to be equal to 0. Okay. Okay. So that equation by itself is may as well be worthless because it's one equation, 3 unknowns, three variables, and all partial derivatives. And so in order to have a closed system, you have to combine this with conservation of momentum. Okay. Oh, it's been a while. I haven't taught fluid mechanics in such a long time, so this is very very fun for me. Although I was thinking about it today, so maybe there's a reason I haven't taught fluid mechanics in a while. And so, of course, this is the form of Navier-Stokes, or the part of Navier-Stokes that usually gives people nightmares. And so, because it's a partial differential equation, and there are a gazillion terms here. All right. By the way, this is only part 1. So this is only part 1 of the momentum equation, because this is the momentum equation in the x direction. Okay. But there's also a momentum equation in the y direction and a momentum equation in the z direction too. Okay. But but the y and z directions look pretty similar. So I'll spare you. So we're just going to look at the x direction. Yeah.
So, your viscosity, is that pressure, is that density?
It's density. Yeah. So
The first one's pressure.
yes. So the pressure, I give it a little tail, and then the density I leave it without the tail, the ponytail. Yeah. So these two here, these ones are density, and then this is the only place that pressure appears. Yeah. Yeah. We'll go over each of these terms. That'll probably be the last thing to do. I love Navier-Stokes. I think solving these problems are a ton of fun. I named my Wi-Fi Navier-Stokes in my house too. My wife, we've been together for almost 11 years now. She still doesn't know what Navier-Stokes is, but her phone connects to it every time we come home. So okay. So of course, a big equation like this, you can kind of see why it's impossible to solve because there's kind of way too many terms. There's way too many things going on. So, we're not going to be solving this equation, in its entirety like this. But we will be solving it under certain niche situations. So, the reason I'm writing this down, I mean, part of the reason I just really like it. I think it's cool. But I also wrote it down just so that we can examine the different parts of this equation. Okay. Because when you have kind of a big equation like this, I think it's kind of more important than ever to kind of understand what each of the terms represent. Okay. And in fact, at least in my opinion, I think that's actually more important than actually learning how to solve these equations. Because once you kind of get to kind of really advanced kind of applied engineering, applied math, you're not really solving really many equations by hand because the problems you're looking at are too complex. Most of the time, you're relying on computers to give you these solutions for you. And so, your job kind of as an engineer, to learning about these things is to kind of understand, what the equations are hoping to obtain and kind of what each term represents, so that you can interpret the solutions a little bit better. So I'm going to do that. So in here, I'm going to basically, we're going to go through what each of these kind of groups of terms represents. And through that, we'll kind of learn a little bit more about fluid flow. Okay, so let's start from the left and go to the right. Okay, so let's start with this term first. Okay. So this term is partial U, partial T. So remember, U is a velocity, right? So U is the velocity in the x direction, and T is time, right? If you look at the entire rest of the Navier-Stokes equations, this is the only term in the equation that has time, okay? And that's on purpose. So this term right here is often called the unsteady term. Okay. And so this term is only active when the flow changes with time. And this term here represents the fact that fluid flow or fluid velocity is able to change with time. Okay. So relatively straightforward. And for the most part, for all the calculations that we're going to do by hand, we're going to assume that term is zero. So we're going to be looking mostly at steady state conditions. Okay. Granted, if you remember, we talked about last Thursday, blood flow is very unsteady. And so because your heart is constantly beating, it's pumping, it's relaxing, it's pumping, it's relaxing, blood flow is very unsteady. So you have kind of rapid changes in the velocity and the pressure as a function of time, right? And so it starts to get a lot more difficult to actually, assume steady state conditions. But when you're solving these equations by hand, you do have to make certain assumptions. Okay. So the next group of terms that we're going to look at is actually the next three terms. So all of these three, they all kind of represent more or less the same thing, just in different directions. Okay. And so in purple there, what I've circled are called the convective terms. And so in a nutshell, these convective terms, if you look at what the derivatives look like here, so you'll notice that all of them have a derivative of velocity with respect to space, right? So we have partial U, partial X, partial U, partial Y, partial U, partial Z, right? So we have all spatial derivatives in this case, right? And so in a nutshell, these terms here represent the fact that velocity can change in space And in fact, momentum can actually be carried through space as well. Okay? Okay. There's kind of a very unique phenomenon that's really only present in fluid mechanics. Is that in fluids, fluids can kind of transport its own momentum, right? So one thing about fluids is that fluids are very good at transporting things. We talked a lot about that on Thursday, right? So your blood flow, its primary means is to transport nutrients and heat throughout your body, right? And that property of being able to transport things is kind of valid for all fluids. Okay? One of the very strange things about fluids is that it can actually transport its own momentum. And so as fluid goes from one point to another, right? Not only is it taking, oxygen, it's taking nutrients, it's taking, stuff with it. It's also transporting its own momentum, which is kind of a recursive idea to kind of think about in your brain. And that's kind of what these terms here kind of represent. And so if you were to ask kind of a seasoned mathematician in terms of, what's the most difficult part of Navier-Stokes to actually solve, it's actually these terms right here. And so the convective terms are the most difficult, mostly because they're the only nonlinear term Stokes. Okay. But for our purposes, very similar to the unsteady terms, for the most part, we're going to assume these terms are zero. And so the entire left-hand side of Navier-Stokes, for most of what we're going to be doing in this class, we're going to assume zero, mostly just for simplicity. Okay. But just know that, once we kind of get to the CFD portion, we get to the computational part, some vascular, your computer is actually computing these terms, and computing these terms is actually quite a hurdle. And so it's actually one of the amazing things about CFD that they can actually do that. All right. Any questions on this so far? Okay. Next, let's look at the pressure term. So this is the only term that pressure shows up. Okay. And so the pressure term, what you're going to see here is that now that we're on the other side of the equal sign, so we're on the right side of the equal sign, the nature of these terms are going to change, right? Everything on the left-hand side represents, how a fluid can change, okay? Everything on the right-hand side here are more kind of forcing terms, external forces, things like that, okay? So this pressure term here represents the fact that pressure or differences in pressure are able to drive fluid. And that's usually the case in the cardiovascular system too. So your heart, when it pumps, it creates a spike in pressure. Okay. And then that spike in pressure is kind of what drives the flow through your cardiovascular system. Okay. And so if that's the case, if pressure is something that can drive flow, then it has to show up in the equations in some way or another. And this is kind of where it shows up. Okay. Next, let's look at G. So G here represents gravity. So gravity, gravity is a type of force. We call it a body force typically. So it's a force that kind of, as long as you have some mass and you're on Earth or you're on some massive planet, you're going to have a force that's exerted on you through gravity. Okay. So fluids are no exception. So fluids have mass, and so gravity can exert a force on the fluid as well. Okay. For the most part, we're going to ignore gravity, but it's not insignificant, right? And so in order for blood to go from your toes back to your heart, it has to overcome gravity. That's something that's pretty relevant. And so that's something that your heart has to overcome when it's pumping blood through your entire system. Okay. All right. And so finally, then we come to this last set of terms. This is the last grouping right here. Okay. So we have a lot of derivatives here. Okay, we have a lot of second order derivatives in particular. Okay. But one thing you should notice is that this is the only place where viscosity shows up. Okay. So these terms here are called the viscous terms. Okay. So remember, we talked about viscosity today. Viscosity is very closely related to shear stresses within a fluid. Okay. And this is where those shear stresses affect the momentum of a fluid. Okay. So this represents how viscous shear stresses So those viscous shear stresses enter into the Navier-Stokes equations through that term on the right there. Okay. All right. Any questions on this so far? Yeah.
I think last class you mentioned how like closer to the heart is like kind of like unsteady, and then like further on like away from the heart it's like steady. So like when you're analyzing something like closer to the heart, would the unsteady term be something you'd actually have to account for?
Yeah.
Oh,
Yeah, very normally it is because if you stick a flow probe, like let's say you stick it in the aorta, which is something that's very close to the heart, you'll see the flow spike up and then go down, spike up and go down. So that's definitely something you can't ignore for the most part. Okay.
I'm sorry. Was that something that's like more like you would analyze through like a program, or is there like the way to like hand calculate that?
For the most part, you would analyze that through a program. It is possible to solve for unsteady flow by hand, but a lot of times it's kind of more trouble than it's worth because you're solving a partial differential equation at that point. And you can do it. It's just, a lot of times what I usually say that the juice is not worth the squeeze. And so you can do it by hand. It's going to take you like 4 hours to do it, or you can just run it in a computer and it'll be done in like 10 seconds. And so, yeah. So a lot of the hand calculation stuff that we're going to do is more to kind of give us intuition, to kind of inform us so that when we do actually look at the simulation results, it'll have better context in terms of, why that looks like a parabola, why is it, fluctuating this way. So, a lot of the theory that we're going to do, a lot of the review is going to be kind of similar to this. We'll do some calculations, just because it's kind of unavoidable sometimes, but, it's mostly to kind of inform our computations. Mhm. All right, any other questions on this? Okay, all right. So I think we only have about 3 minutes left. So I think I don't really want to start the next thing, but I did want to make sure I get to Navier-Stokes today. And so, this is going to be our equation. And so what we're going to do on Thursday is that we're going to take this equation, we're going to start to apply assumptions onto it. And then what you'll see is that with the assumptions, we'll be able to cross out a lot of these terms here. Okay. So actually we'll be crossing out all of these terms. And then after we cross out all of those terms, we'll get something that we could actually solve by. Okay. All right. So today, very quick crash course in fluids. And so, hopefully you've seen some of this stuff. Maybe it brings back memories. I won't say whether they're good or bad memories, but you know, hopefully it's stirring some things up. And then Thursday we'll kind of continue on with this. And then we'll kind of move on to more cardiovascular stuff. All right, so thank you guys for coming today. Hope you guys enjoy the rest of your day, and I will see you guys on Thursday.
I'm still on the wait list. I'm trying to just pull at straws to see if there's any possibility.
So I mean, if people drop this week, it's still possible. So we have until the end of this week. So I'll keep an eye on it until the end of the week. But I asked the department to add everyone, but they said it's class only on 37. So I can only add 30. You can stay on the wait list until then. And if people drop, then I can ask to add more. But right now, we only have 7.
Yeah, I was running numbers with online and in class. There was 21 open seats. Physically in the room, you take the 13 here, one of those is you, that's 12.
Yeah.
There's 9.
Mhm.
I'd still be out of the list. I don't need the class to graduate.
Yeah.
I just really enjoy it.
So I can still add you to the Canvas site. And so if you want to just kind of follow along, I mean, you're welcome to come. I mean, it's with the exception of the exam day, I mean, there's gonna be more than enough seats here because it's always like 20 people in Zoom. So I can always do that. And then and you can just kind of follow along that way. But I'll keep an eye on the wait list for the rest of the week, see if people drop. But the number they told me was 37. So we can keep it under 37.
Yeah. Do you think if I talk to like Dr. No or something, I could try to?
I've already talked to him. I've already kind of pleaded my case, but I mean, it wouldn't hurt, but that's the number he told me for this class.
All right. I think I don't know if I have access.
Oh, I don't think so. Just email me. Just email me, and I'll give you access to the site. Yeah.
Actually, a quick question.
Sure.
I was just wondering, when's like the last day of the ad drop period?
It's Monday technically, but for all intents and purposes, it's Friday because we have to set things in motion to like add people, and then they give us until Monday just for that process to finish up.
I remember they said they like extended it for the strike and then they said like move it back.
From what I understand, it's Monday from what I checked.
Okay, for sure. I was just wondering, because I'm like kind of between a couple of electives I want to choose right now.
Yeah.
But I'm definitely gonna keep this class.
Okay, yeah. Yeah, I think it's still Monday. So I mean, I guess technically you could wait until then to make a decision, but I definitely wouldn't push it past that.
Okay, for sure. Thank you. Appreciate it.
This will be a fun one. I have no good reason to be kids.
Okay, I appreciate that.
It kind of sucked for me because the courses that I had too many waitlisted at the same time to put this on too.
I see. Yeah, there's a limit. There's a limit on that.
So I was waitlisted in CFD and in CATIA.
Uh-huh.
So once those finally cleared, I hopped on this one. I'm like, oh.
Yeah, I saw you hopped on kind of late.
Yeah.
I hope we can do this. That's why I waited until Friday to get the list. And then that's when I gave the list to the department. So yeah, only 7. So
Yeah.
Thank you. Yep. First assignment, I need to make it first, but definitely not sooner than next Friday. So it'll be I'm hoping to put it out by tomorrow. It'll be mostly on the fluid stuff, and so it'll probably be due next Friday, most likely. If not, if it covers a bit more, then I'll probably push it back until the following Tuesday. Yeah, but no sooner than next Friday. Yep.